Are you struggling with how to efficiently manage and conserve IP space in Google Kubernetes Engine? While Kubernetes has a significant appetite for IP space and configuration might appear quite challenging, a solid understanding of the configuration points can go a long way in helping you better handle your precious internal RFC 1918 IP addresses. As you work with Google Kubernetes Engine, you'll primarily be dealing with standard clusters, a hands-on job where you'll be managing your own node pools. Autopilot mode is like going on cruise control. Less work, maybe, but also less control. Regardless of the GKE approach, you'll need to keep an eye on pod CIDRs and service CIDRs, but we'll focus on the standard GKE path today. Alright, our journey begins at the standard cluster configuration screen. We'll be mostly sticking to the defaults, except for a little bit of networking discussion and tweaks. Let's start with one of the most important settings, the maximum number of pods per node to optimize the distribution of our limited cluster IP addresses. The pods per node directly dictates how much IP space is allocated to each node, regardless of that node's actual pod count. For instance, a subnet mask of 24 means 254 IP addresses. Kubernetes, by design, needs 2 IPs per pod. Hence, we have our max of 110 pods, roughly half of 254. What if we had a leaner setup? Well, we could opt for a 26 mask, allowing around 30 pods per node, which is more than enough space for many applications. Typically, you'll want the automatic secondary range setting on, as it'll keep things efficient without any manual effort. You can leave these fields blank to pick up on the default values. Alright, now that we've got the node level details down, it's time to roll up to the cluster level networking for some extra configuration. Like the node pool override, we can cut down on our pods per node at the cluster level. The adjustments we made to the pods per node means we'll be dividing up our IP ranges into smaller, more utilized slices, but we're not done yet. We still need to allocate cluster address ranges for our pods and services. Time to dust off our IP calculators to estimate how many pods and services that we can support under these settings. For instance, let's consider splitting this 192.168 RFC 1918 space in half. Now this will give us a sizable IP space of approximately 32,000 IPs. Therefore, we have about 16,000 max pods for this cluster, which is almost certainly an over-provisioning. The services range is by default pretty large as well, as we likely won't need 32,000 services. For the pods, we need to specify a mask of up to /21, but we can go up to /27 for the services. At just about 30 services, though, this would be a pretty small max. We might want something closer to a /22 mask for supporting up to about 1,000 services. Note that we have automatic secondary ranges enabled, which means both our cluster level and node pool level specifications will be effectively managed for us. By making the tweaks that we've walked through in this video, you'll end up with a cluster that's up to hundreds of times more IP efficient than the default settings. However, this isn't the only IP space consideration. More broadly, if you're still struggling with a lack of IP addresses in your project, you can consider a few options. Firstly, you can use network peering to connect the VPC with the Kubernetes Engine cluster to other VPCs. This can give you something close to dual use of the RFC 1918 space. You can also utilize spaces like RFC 6598 and RFC 5735 if you're particularly short on the 1918 space and need some additional room. As a last resort, using public IP space is also supported. We hope this video has been helpful, and we thank you for watching. We'll keep an eye on the comment section for any questions and remind you to please enjoy responsibly.